So in this example, we're given that p of x equals x to the fifth power minus 3x to the fourth power minus 3x cubed plus 9x squared minus 4x plus 12. In part A, we want to use the rational zeros theorem to determine the possible rational zeros of p of x. In part B, what does Descartes' rule of signs tell us about the number of positive real zeros and the number of negative real zeros? In part C, we want to solve p of x equals 0. So part C is really what it is that we're trying to do. We want to solve, and so we're going to use the rational zeros theorem and Descartes' rule of signs to help us achieve part C. Okay? So in part A, we're going to use the rational zeros theorem. So remember, if a rational zero, p over q, is a zero of our polynomial function, then p has to be a factor of the constant, in this case 12, and q has to be a factor of the leading coefficient, which in this case is 1. Okay? So the possible values of p is going to be the factors of 12, which would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12, because 12 can be divided by all of these values. Okay? The possible values for q is just going to be plus or minus 1. The only thing that 1 can be divided by evenly is 1 or negative 1. Okay? So the possible values of p over q are going to be all of these p's divided by plus or minus 1. The only possibility for q, well, plus or minus 1 divided by plus or minus 1 is just plus or minus 1. Similarly, plus or minus 2 divided by plus or minus 1 is plus or minus 2. Plus or minus 3 divided by plus or minus 1 is plus or minus 3. And plus or minus 4, and plus or minus 6, and plus or minus 12. So our answer to part A, these are the possible rational zeros. So there's 2, 4, 6, 8, 10, 12 possible rational zeros that this polynomial function could have. Okay? Part B. What does Descartes' rule of signs tell us about the number of positive real zeros and the number of negative real zeros? So looking at our polynomial functions, we want to see how many variations in signs there are. Now, first of all, notice that this is already written in decreasing order. Our leading coefficient's positive, so we're starting with positive, and we switch to minus 3x to the fourth, so that's one variation in sign. Going to the next term, it stays negative, so there's no variation in sign there. Then it switches back to positive, so there's our second variation in sign. Then it switches back to negative, so there's our third variation in sign. Then it switches back to positive, so there's our fourth variation in sign. So Descartes' rule of signs tells us that we could have up to 4 positive real zeros, or it could be less than 4 but decreased by an even integer. So 4 minus 2 would be 2, and 2 minus 2 would be 0. So we could have either 4, 2, or 0 positive real zeros. Okay? Now those don't have to be the rational ones. But there's only going to be at most 4 positive real zeros, or 2 or 0. Okay? Now in order to find the possible number of negative real zeros, we have to find p of negative x. So I'm going to do that down here. I'm going to find p of negative x. So that's going to be negative x to the fifth power minus 3 times negative x to the fourth power minus 3 times negative x to the third power plus 9 times negative x squared minus 4 times negative x plus 12. Again, just substituting negative x for every x in our polynomial function and simplify. Okay, so negative x raised to the fifth power will be negative x to the fifth power. Negative x to the fourth power is the same as x to the fourth power times negative 3 is going to be minus 3x to the fourth power. Negative x to the third power is the same as negative x to the third power times negative 3 is going to be plus 3x to the third power. Negative x squared is the same as x squared times plus 9, so plus 9x squared. Minus 4 times negative x is going to be plus 4x, and then we still have plus 12. So we have negative, stays negative, so no variation in sign. Changes to positive, that's one variation in sign. Stays positive, stays positive, stays positive. So there is only one possible negative real zero. So we could have at most one negative real zero. So Descartes' rule of signs tells us that we could either have 4, 2, or 0 positive real zeros, and we could have one negative real zero. In fact, what this tells us is that we will have one negative real zero. It may or may not be one of these rational zeros because this negative zero could be irrational, but there will be one negative real zero. So now we want to solve, and so we're going to use what we've learned from parts A and part B to help us solve part C. We're going to do part C on a different sheet. So in part C, we have our polynomial function x to the fifth minus 3x to the fourth minus 3x cubed plus 9x squared minus 4x plus 12. We're setting that equal to 0, and we want to solve that. So in other words, we want to find the zeros of our polynomial function. So as I did in our previous example, I'm going to kind of help move things along a little bit. If I look at the graph of our polynomial function, that will help me determine which of our possible zeros to check. So I'm going to look at the graph. I'm going to do a zoom 6. And so here is the graph of our polynomial function. Now this is not the best graph, but it does do what I need. I can see from the graph it looks like we are crossing at negative 2, at positive 2, and at positive 3. So it looks like the x-intercepts are negative 2, positive 2, and positive 3. So those would be the three values that I want to check to make sure if they're zeros of the function or not, or solutions to our equation. So again, it's looking like negative 2, positive 2, and 3 are zeros of our function, and so I can use that to help me figure out the rest. Now, just to bring this in, notice that we did have plus or minus 2 as possible rational zeros. We also had positive 3 as a possible rational zero. So all of those look like pretty good prospects. Okay, so I'm going to use synthetic division, and I'm going to put negative 2 out here, and I'm going to put my coefficients 1, negative 3, 9, negative 4, and 12 under here, and I'm going to go through the synthetic division process. Okay, so I'm going to drop down the 1. Negative 2 times 1 is negative 2. Negative 3 plus negative 2 is negative 5. Negative 2 times negative 5 is positive 10. Negative 3 plus 10 is 7. Negative 2 times 7 is negative 14. 9 plus negative 14 is negative 5. Negative 2 times negative 5 is positive 10. Negative 4 plus 10 is 6. Negative 2 times 6 is negative 12. And 12 plus negative 12 is 0. So that's nice. So what this tells me is that the x to the fifth minus 3x to the fourth minus 3x cubed plus 9x squared minus 4x plus 12, that factors into x plus 2, because negative 2 we just showed was a 0, times, now it started with x to the fifth, so this is going to be 1x to the fourth minus 5x cubed plus 7x squared minus 5x plus 6. So our original polynomial factors into x plus 2 times this. Okay, now x minus 2 should also be a factor. So in other words, this should factor into x plus 2 times x minus 2 times something. And so to figure out what the something is, I'm going to divide by x minus 2, which means I put a 2 out here, and I'm going to run through the synthetic division process again. Drop down my 1. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. 7 plus negative 6 is 1. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. And 6 plus negative 6 is 0. So again, we got a remainder of 0, which means x minus 2 is in fact a factor of this. So this x to the fourth minus 5x cubed plus 7x squared minus 5x plus 6 factors into x minus 2 times, now again we had x to the fourth, so inside here now we're going to have 1x cubed minus 3x squared plus x minus 3. Now I'm going to check to see if 3 is a 0, and it looks like it should be, which means this should factor into x plus 2 times x minus 2 times x minus 3 times something. So let's put the 3 here and run through again. Drop down the 1. 3 times 1 is 3. Negative 3 plus 3 is 0. 3 times 0 is 0. 1 plus 0 is 1. 3 times 1 is 3. Negative 3 plus 3 is 0. That's a remainder. So again, rewriting my factors, the x cubed minus 3x squared plus x minus 3 factors into x minus 3, because 3 we just showed the 0, times, now again we had x cubed here, so this is going to be 1x squared plus 0x plus 1 equals 0. Now, so we did have 3 zeros in this case. We had 1 0 was negative and 2 was positive. If you'll remember from our Descartes rule of signs, we said that we had to have one negative real 0, and we could have had either 4 or 2 or 0 positive real zeros, and right now we have found 2 of those positive real zeros, and those are the only rational ones. Now to finish solving, notice we have this factor x squared plus 1, okay? So either x plus 2 equals 0, or x minus 2 equals 0, or x minus 3 equals 0, or x squared plus 1 equals 0. Well, this gives us that x equals negative 2, which we already knew. This gives us that x equals positive 2, which we already knew. This gives us that x equals positive 3, which we already knew. Okay? But if x squared plus 1 equals 0, then we could subtract 1 from both sides and say x squared equals negative 1. And then we can take the square root of both sides, and when we do that, we put in our plus or minus, and we get x equals plus or minus the square root of negative 1, and that is plus or minus I, because the square root of negative 1 is I. So we end up with 5 zeros. Those zeros are negative 2, 2, 3, positive I, and negative I. So the zeros of our polynomial function are these 5 zeros here, and this is the solution to the equation p of x equals 0. Again, notice this is in line with what we discovered from both the rational zeros theorem and the Descartes rule of signs.